Hello, seekers. Welcome to the eighth video of blockchain series. And the last few videos, we spoke about the idea of proving the security of blockchain in mathematical terms. And specifically, in the last video, we refreshed our knowledge on probability. And we'll quickly summarize that, and then we will get back to the context in which we brought in these ideas of probability, and we'll take it from there. So we looked at two distributions of probability: the binomial distribution, and in essence, using the binomial distribution, we were able to quantify the probability of a specific event, and in this example, we took the scenario of coin tosses, and wherein a coin was tossed n times or n trials, and each toss had a probability of p for a head to turn up, right? So with that, we were able to generalize the binomial distribution, which was the probability of getting x heads in n trials can be quantified the following way, right? For instance, p of x is equal to 1 means it's a probability of getting one head in n trials. Now, while binomial distribution helped us answer questions like these, which is like probability of getting x number of heads in n trials, we also extended the binomial distribution. We stretched and we took it to what we called as the Poisson distribution. And the key ways in which we stretched that was, we took n to be infinite, wherein the number of trials is not finite anymore; it's close to infinity, and also the probability of that event occurring is also close to zero, right? And when we applied these two constraints, or when we applied these two considerations, we saw how we were able to extend this into something like this, right? P of x equals x is actually lambda to the power of x times e power minus lambda over x factorial. And E is the Euler number, approximated to 2.7, and lambda is the expected value of the event, and lambda was equated to n times p, right? Now, this is how we arrived at the Poisson distribution, and Poisson distribution can help us answer questions like these, right? If you were to know, right, if you have a coin which has a very low chance of a head to turn out, and if you keep tossing that coin infinite number of times, what is the probability of getting a head in the xth trial? Right? So questions like these can be answered through Poisson distribution, right? So if the coin is so biased that it doesn't turn up as a head very often, which means that the probability p is so zero, is close to zero, then p of x equal to 1 gives a probability of getting ahead of the very first trial, right? So that's what Poisson distribution helps you answer. I hope you get that difference between the two. This question is different as compared to this specific question, right? So we will soon make use of this in the context of blockchain. But before that, we will quickly summarize the blockchain context as well, all what we have gone through so far. So in the previous videos, we went through the scenario of a blockchain which had the chain was split into two parts, which was like there were I blocks and then there was Z blocks, and then we derived the formula for the probability that a dishonest node can succeed in building a blockchain of length I plus Z plus 1. Right, when it attempts to tamper with a transaction that is on the ith block, or that is at least Z blocks deep. Right, so when a transaction has to go back and when a node has to go back and change tamper with a transaction that is Z nodes deep, we found that the probability of that succeeding was Q by P over times to the power of Z plus 1, right? So this is the probability by which a dishonest node can build a longer blockchain, which is the current blockchain plus one additional block, right? We derived this in the previous videos. Now, what happens when we equate Z to 0? When Z is 0, it means that Wi turns out to be Q by P, which is nothing but the probability that a dishonest node succeeds in tampering with the current block, right? Which means that it doesn't have to go Z node deep. When Z becomes 0, it is trying to tamper with the current block, right? So that is the probability. So Q by P is the probability that a dishonest node would succeed in tampering with the current, Q by P is the probability by which a dishonest node can succeed with tampering with the current block, right? So with this, let's try to map it with the Poisson distribution, right? Where Poisson distribution is going to come into play here. In Poisson distribution, we took the scenario of a coin toss. Right, we took the scenario of a coin toss where there are n trials where n tends to infinity, and you have the probability of heads turning up to be P. And given that, we knew that the probability of getting a head on the X trial can be equated to a Poisson distribution here, right? So in this case, the probability is P for each of these boxes because each box is a trial, and the probability that you will get a head in the Xth trial can be equated to this Poisson, can be derived from this formula. We can apply the same concept here in a blockchain as well. Now, let's consider a blockchain, an infinite blockchain, and so that's what we showed here. We have shown here, and it starts from block 1, 2, 3, and all the way up until infinity. It's an infinite blockchain. And what if a dishonest node tries to tamper with a transaction in the current node? Let's say it tries to tamper with the transaction in the first node. There are two possibilities: either it can succeed or it cannot succeed. When say it cannot succeed, it means that one of the other honest nodes have built a longer blockchain. So in that case, the dishonest node tries the second trial, right? It tries to tamper with the second one. If it either succeeds or not, then it tries the third one, right? So a dishonest node continuously tries to think about a dishonest node that continuously tries to tamper with a particular transaction. Now, this whole thing can be mapped to a coin toss problem, right? So just the way we can look for, you can use Poisson distribution to find the probability of a head appearing in the Xth trial, you can apply Poisson distribution to find the probability that a dishonest node would succeed in the Xth block, right? In this case, trial is nothing but a block here, right? So P of X is equal to 5 means the probability that a dishonest node would succeed in tampering with a block in one of the 5 blocks, right? So that is what P of X is equal to X means. So, and in this case, the probability of a dishonest node succeeding for a particular block is Q by P, right? So that's what we derived here. So the dishonest node tries to tamper with the current block. It might succeed or fail. Then if it fails, it tries to tamper with the second block. It might succeed or fail. Else it might go to the third block, and so on. So the probability that a dishonest node would succeed in the Xth trial, and each trial is considered one particular block, it can be expressed through this Poisson distribution, right? Now let's keep this handy, and now we will come back to the original problem where which motivated us to learn or refresh our skills on probability. The original problem is that actually motivated us to refresh our skills in probability is to find out that ideal number of blocks that the receiver has to wait after a transaction is being made, right? So let's say that a node gives some money to another node, and immediately tries to come back and tamper with that particular block and convince the other nodes that the transaction never happened. If that node tries to do it here, and the reasonable strategy that the receiver can adopt is to wait for Z nodes, and even after Z, if the transaction is there, the receiver would make use of that money. And we want to arrive at what is the ideal value of that Z. An ideal value of that Z is the one such that the risk is negligible from the receiver standpoint, right? That is how we need to choose Z. If the probability of tampering is extremely small after Z, then it is reasonable for the receiver to start making use of the money after waiting for Z blocks, right? So we want to determine this Z here. So how do we quantify this risk? Before we show that risk is negligible after waiting for Z blocks, we will first have to mathematically quantify that risk that Z is exposed to. Now, so that risk we can quantify that risk in two parts, right? Now, what does that risk mean? The risk is that the node has the sender has attempted to let's assume that the sender has somehow tampered with the transaction before the Z blocks, right? Now, to do that, what all has to happen? There are two things that needs to happen here, right? Now, one is this dishonest node will have to succeed in tampering with this block, right? It has to succeed in tampering with this block because this is where the transaction is. And this dishonest node has Z attempts to tamper with it, right? Either it can tamper it because the receiver is going to wait for Z nodes, right? So which means that the sender has Z trials to tamper with this node. One thing can happen is on the very first attempt, it can succeed and tamper with it on the first trial itself. If it misses that, which means that if a honest node's transaction is faster, then it has lost the first trial. The dishonest node will have the second attempt to tamper with this. If not, the dishonest node will have the third attempt to tamper with it. At the max till Z, right? Because after Z, it is assumed that the risk is negligible, right? So the first part is we want to know the dishonest node has to succeed in tampering with that block, and it has Z attempts to do that, right? The second part is when it tries to in each attempt, it actually has to successfully rebuild the entire chain. If you recall here, the first part is if the dishonest node tries to tamper with here, it just has the current current chain to rebuild. If it misses the first opportunity, it means that it has to revert the transaction, which is at least one block deep. And if it misses that opportunity too, and if it is actually here, if the dishonest node has missed two opportunities, then here it has to go 2 nodes deep, right, and so on. So in essence, there are 2 parts to this risk. That's what we've tried to capture here. The first part of a dishonest node trying to succeed in tampering with the block, it has a Z trials, right? It has Z trials, and that if you recall can be answered through the Poisson distribution, right? And that's what we have shown here. This one tells gives the probability that the dishonest node will succeed in the first attempt itself. This one quantifies the probability that the dishonest node will succeed in the second attempt, and this is the third attempt, and so on. And this is what we have given all up until the kth node, and we are considering an infinitely long blockchain, and that is where Poisson distribution is going to be applicable here, right? So the first part of the risk, which is about quantifying the probability of a dishonest node succeeding in the xth trial, right, in tampering with the block in the xth trial, is quantified through this component. Now the second part is, in each of the steps, right, the dishonest node has to successfully rebuild the chain, right? If the dishonest node succeeds here in tampering with it, then it only needs to go one node deep, and the probability of that is Q by P, right? If it misses that, and if the dishonest node manages to tamper with it in the second attempt, it means that it has to go one node deep. So which is the probability of that succeeding is Q by P to the power of 2. So if you recall that, this whole thing is derived from this formula, right? Probability of a node succeeding in reverting a transaction that is Z nodes deep is given by this formula, right? So that's what we have given till Z. When it is at Z, when the node is when the dishonest node has managed to tamper with it only in the Zth trial, and it has to go Z node deep to make that transaction deep, because the transaction is still here. So the probability is going to be this one. What about after Z? After Z, we can consider the probability to be 1. The probability that the dishonest node has the probability that the dishonest node has can successfully rebuild the chain can be considered 1 for any nodes after Z, because we intend to quantify the risk of the receiver after waiting for Z blocks. So we can assume that the dishonest node has we can consider that the dishonest node to take at most Z blocks to catch up, which means that we can assume that the dishonest node has succeeded. To be to be conservative, we can assume that the dishonest node has succeeded and it takes at the most Z attempts. So which means that after that, yeah, whatever has done, it has succeeded, and which means that the probability it doesn't have to catch up anymore. It has already caught up. The transaction is already tampered with. Let's assume that after Z nodes, because the receiver is going to start making use of this money, and our intent is to quantify the risk that the receiver is exposed to, right? So we will take the maximum of keeping it as 1. We'll assume that after Z, the dishonest node has actually succeeded in tampering with the transaction. That's why you see the value of 1 after the Z block, right? Now with this, if we quantify the whole risk, which is nothing but it's going to be a multiplication of these two and the entire sum. That's what we have given here. So it is the sum of the Poisson distribution times the probability that the node can actually catch up at each trial, and that's what is the total risk, right? So what we have done here is we have multiplied the Poisson distribution times the probability. And this probability, we have assumed that after Z blocks it is 1, because the node takes at most Z blocks to tamper with, and it's the entire sum here, right? So this is the total risk that the receiver is exposed to, correct? Now, our point is not to get to the total risk, but we want to only quantify the risk after the Z block, because the receiver is anyway going to wait for Z blocks, right? And it is sufficient if we just quantify the risk after the Z block, right? Because that is the risk that the receiver is going to be exposed to. So how do we equate this? So the total risk after waiting for Z blocks is nothing but 1 minus this sum of this Poisson distribution times 1 minus Q by P times the Z minus K. Why is this? What is the rationale behind this? See, this total risk is only the portion of the overall outcome, right? This risk means that this is the possibility that a node will be, a dishonest node will be able to tamper with. So 1 minus this whole value is the probability that the honest nodes will succeed, right? 1 minus. So that's what this 1 means. So we're actually subtracting the 1 minus the whole thing here, right? So out of the overall outcome, we are trying to exclude the probability that the honest nodes will succeed. So we are trying to exclude that part here. The second part is we are also trying to exclude the probability of this part, right? We don't need to care about this probability because the receiver is anyways waiting for Z nodes. So we can ignore this part also, right? Because end of day, it is the risk is nothing but this component, because the receiver is anyways waiting for Z nodes. So that is where no, this equation gets transformed to this, and you have a 1 minus in two places to consider both. The first one is to exclude the possibility of honest nodes succeeding, and the second one is to exclude the possibility of this part, right? The risk before the Z nodes. Now, the idea here is that, so this, now we have eventually quantified the risk for a node, that a receiver is exposed to after waiting for Z block. So this is the probability. Now, from this, let's try to find that ideal value of Z, right? Now, we'll try some values here, and hopefully, this should give us a context here. Now, when you take the Z for when you take Q to be 0.1, which means that 10% of the compute is going to be controlled by the dishonest nodes. When you take the value of Z to be 0, you get a probability of 1.000. When you take a Z to be of 1, which means that when a dishonest when the receiver waits for one node, waits for one block, right? The probability of that of the dishonest node succeeding immediately drops to 20%. When the transaction is made immediate, it means that the probability is that that there is a good chance that the dishonest node can succeed with tampering. But the moment Z becomes 1, you can see the probability to significantly drop to 0.2. And if the dishonest node waits for 2 blocks, when Z is equal to 2, if the receiver waits for 2 blocks to confirm the transaction, the exposed risk comes down to even lower. It becomes 0.05%. So, and you might see this very clearly, right? The longer that the receiver waits to confirm the transaction, the probability, the risk exposure is significantly reduced. The risk exposure completely goes down, and when you go to Z is equal to 6, it is completely negligible, right? The risk exposure has come down to close to 0.00024. So this makes it clear that the reasonable strategy for Z can be somewhere like around for your probability to be as negligible as 0.001, the receiver can wait for 5 blocks to be built. After making a transaction, after receiving some money, in a network where 10% is controlled by the dishonest nodes. Even if the compute is higher, even if the value of Q is higher, of let's say that 20% of the nodes are now dishonest, the 20% of the nodes are controlled by dishonest nodes. Even in that case, your receiver, if it can wait for Z block to be built, the probability comes down to 0.001. So this is a strategy. We wanted to arrive at this value of Z. Now, what is that ideal value of Z that a receiver can adopt to wait for until making use of that money after a transaction is made? So that is what we intended to calculate, and I hope I was able to accomplish that in this video. I think with this we come to the end of the blockchain series, and I hope these sessions were helpful in terms of getting you the intuition behind why the design of blockchain is the way it is. And I hope we were able to explain that both from technical terms as well as from the mathematical standpoint.
Did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.